Hi everyone, this is Professor Monty. If you remember last time, what we did is we looked at how to find absolute maximum and minimum values. Well, today what we're doing is we're going one step further and applying that to economic problems. So you can see this is section 3.5 optimization, meaning find absolute max and mins for business, economic, and general applications. Now I'm only doing the business and economic applications. So I wanted to stay away from all the geometric type of problems. So let's kind of just jump in and get started. The first problem we're going to do, let me show you what the problem is. It's problem 30 out of the book. It gives us R of X, which is revenue, and it gives us that function, gives us a cost function, and it says assume that R of X and C of X are in thousands of dollars and X is in thousands of units. Well, what this question asks us to do, it's a whole series of problems where they give us revenue and cost. But what the question is asking us to do, it says find maximum profit and the number of units required to produce. To find maximum profit. Okay, so of course this problem is twofold. One, we want to find out, we're trying to maximize our profit, so we want to find out what that maximum profit's going to be. But we also, more importantly actually for us, is we have to figure out how many units to produce and sell in order to reach that maximum profit. Okay, and so first off, recall profit is revenue minus cost. So revenue, all the money coming in, minus cost, all the money it costs to produce or purchase the items. That's where we're starting from. That's what we're trying to maximize. So let's write down our goal, maximize profit. And we'll write profit, revenue minus cost. And so let's just go in and we'll actually do that right here. So R of X, revenue function, 100X minus X squared. That's revenue minus cost, 1/3 X cubed minus 6X squared plus 89X plus 100. So that's my revenue minus cost. Remember, revenue and cost are in thousands of dollars, X is in thousands of units. We'll have to remember that when we write our answer. So I've got my formula, let's call it P of X now because we're all in the variable X. I need to distribute that negative through to everything. So if I just write it out as one big piece, it's 100X minus X squared, but then minus 1/3 X. I'm thinking I left something out. It's 1/3 X cubed, isn't it? 1/3 X cubed minus, well, I'm distributing, so plus 6X squared minus 89X minus 100. And let's see, like terms. We have the 100X and the minus 89X. We'll be able to put those together. We have the minus X squared and the plus 6X squared. So when we combine like terms, we'll go in descending powers. We get negative 1/3 X cubed. And then let's see, the X squared minus 1X squared plus 6X squared. So we have plus 5X squared. And then 100X minus 89X is going to be plus 11X minus 100. Okay, so notice right now, if X is 0, I mean, we've sold 0 units, 0,000 units literally, our profit's going to be negative 100. Well, that's our fixed cost. So that makes sense. We should always have a negative profit as our constant, because if we don't sell any units, of course, we're going to be out any of our fixed costs. Now, it might be 0. That's possible as well. But we shouldn't have a positive profit if we don't sell any units. Okay, so we're set up. We're trying to maximize this function. So as always, I take the derivative and set it equal to 0. Bring down the 3. I'm going to get negative 1X squared, or just negative X squared, plus 10X plus 11. And I set that equal to 0, because remember, we're looking for the critical values, wherever the derivative is 0 or undefined. I don't like the negative x squared, so I'm going to divide both sides by -1. So I get positive x squared minus 10x minus 11 is equal to 0. Now, bear in mind something. When I'm looking at this function, I'm trying to solve this. It's a quadratic. It's got an x squared with an x in there as well. I have to set it equal to 0 and factor. I'll see students who want to add the 11 to both sides and then factor out an x. There's not a rule that says if two things multiply to 11, one of them has to be an 11. But there is a rule, the property of zero products, that says if two things multiply to equal 0, one of them has to be 0. So we need two numbers that multiply to -11, add to -10. So it's x minus 11 and x plus 1. And so I set each of those equal to 0, either x minus 11 equals 0, which would mean x is 11, or x plus 1 equals 0, which is x equals -1. And hopefully a lot of you go straight there from the factoring. You say, well, if x plus 1 equals 0, I know x is -1. But if you want to set it equal to 0 and then solve, obviously you're welcome to do that. Remember, x is thousands of units made. We can't produce -1,000 units. No negative units. We'll say no negative number of units. Okay, so I've got this x equals 11. My guess is that 11,000 units produced is going to maximize the profit. But here's where I have to be careful. I don't know that's going to maximize the profit. All I know is that that's a critical value. Well, I can look to the left of 11 and look to the right of 11, make sure the function's going up to the left and down to the right, first derivative test, or I could use the second derivative test to see if that's actually a maximum. All I know so far is it's a critical value. I don't know it's a maximum. So what I'm going to do is I'm going to go p double prime of x over here. And where I'm looking is right here before I divided by -1, the original derivative, and I'm taking the derivative of that. So I'm getting -2x plus 10. That's where I plug in my 11. P double prime of 11 is -2 times 11 plus 10, -22 plus 10. Now it's -12, but I don't care about the number. I just care that it's negative. Because remember, if the second derivative is negative, it means the graph's concave down. So the graph's concave down at 11, since that's a critical value, that must be a maximum. So therefore, the three dots in the triangle mean therefore, we do have a maximum at 11. So we've proven that the maximum happens at 11. Assuming we've done everything correctly, that one property that we saw earlier that said if there's only one critical value in my domain, which in this case, x has to be 0 to infinity, there's only one critical value in there. Well, if it's concave down, it has to be a max. If it was concave up, it'd have to be a min. But so we know the max does occur at 11,000 units. So we're halfway done with this problem. The rest is simpler to do. So we say absolute max at 11,000 units produced. That answered part of the question. The other part of the question, we'll box that since that's part of our answer. The other part of the question asked us, what is the maximum profit? Well, we take that, plug it into the profit function. So we're finding P of 11. Now, if you get a 0 here, it's probably because you plugged it into P prime. We're not looking for the derivative is 0, or we're not looking, we know the derivative is 0 when x is 11. That's how we found the 11. We're looking for what the profit is. So we go back to the original profit function, which is, let's do this one in green. Here's my profit function. That's what I'm plugging into. So I'm going to go, I'm just plugging in 11 for x. So P of 11, -1/3 times 11. I'm going to have to go back and forth. Plus 5x squared plus 11x. Plus 5 times 11 squared plus, was it 11x? It was minus 100. All right, so there's my profit function. Let's make sure I have that right. 1/3 x cubed, plus 5x squared, minus 1/3 x cubed plus 5x squared plus 11 times x minus 100. Perfect. And then I'm just going to plug this straight into my calculator. We'll put the answer right here. So let's see. I get -1 divided by 3. I'm just going to hit equal. So I get -0.3 repeating times 11 cubed plus 5 times 11 squared plus 11 times 11 minus 100. And I get 182.333 repeating. 182.333, and that's repeating. Now, the reason I go out to 3 decimal places is because the question was saying to me, hey, that's in thousands of dollars. So my answer is maximum profit, 182. So I multiply this by 1,000, means I move the decimal 3 places, 182,333. And if they wanted me to go to the nearest cent and 33 cents, if they wanted me to go to the nearest dollar, just 182,333. But there's my answer. So I found the maximum profit. I get a maximum profit of 182,333.33 when I produce 11,000 units. So that's the idea. That is how we do these problems. I have 3 applications to do today. And so we'll just look at them in turn. We're just getting practice of what we've learned in the previous section. Okay, so we're going to put the next problem about right here. So let's go get it. It is problem 32. So let's copy this one. We'll go back and paste it in here. A lot more steps in this problem, as you can see. Maximizing profit. Rags Limited, a clothing firm, determines that in order to sell X suits, the price per suit must be, and they give us a price function. It also determines that the total cost of producing X suits is given by, and they give us a cost function. Find the total revenue, find the total profit, how many units must be produced in order to maximize profit, what is the maximum profit, what price per suit will maximize profit. Now, knowing both C, how many suits to produce in order to maximize profit, that's important. Because if we don't produce enough, we're going to sell out, and we would be able to sell more suits and make more profit. If we sell too many, they're not going to sell at the price that we have, and we might end up losing money on those suits. So we have to know how many suits to produce. And then E is probably more important because we have to know what price to set the suits at in order to sell the number of suits we're hoping to sell. Okay, so let's go through this. Notice this time it says find the total profit. Ooh, total revenue is part A. Well, revenue, last problem it gave us revenue. This time it doesn't, but remember revenue, all the money we bring in, that's price times quantity. We usually just write R equals P times Q. Okay, so they give us a price function this time. So when I do revenue, and we'll put it in terms of X, it's price 150 minus 0.5X times quantity. Well, quantity is the number of suits, that's X. So that's my price times quantity. So I multiply that out. I'm just going to distribute, of course, and I get 150X minus 0.5x squared. There's my revenue function. That was the first thing they asked us, find the revenue function. So just so that we have it all in one piece, I will put it again right here. There's my revenue function. B says find the total profit. Well, remember, profit is revenue minus cost. Well, we have revenue, 150x minus 0.5x squared. minus cost, they gave us that as 4,000 plus 0.25x squared. All right, and as we go through here, we're going to do P of X for profit. Now, sometimes since we're using little p for price, sometimes they'll use pi of X for profit, because pi, of course, is the Greek letter for P, but we'll just go ahead and leave it as capital P of X. Hopefully we'll be able to tell the difference between those. So I'm going to do P of X. I have to distribute that negative in there. So I'm going to get 150X minus 0.5x squared minus 4,000. Remember, we talked last time, the constant should be negative in profit, minus 0.25x squared. Remember to distribute that negative to the x squared portion, because when I put these x squareds together, I'm going to get P of X negative 0.75x squared plus 150x minus 4,000. All right, there's my profit function. So that's part B. C says how many suits must be produced and sold in order to maximize profit. Well, we're trying to maximize what I just boxed. So C, to maximize profit, what do? You find the critical values by taking the derivative. Now, 0.75 times 2, that's 1.5. So negative 1.5x plus 150. That's going to come out nicely. Set that equal to 0. Let's just subtract the 150. I get negative 1.5x equals negative 150. And then I divide by negative 1.5. Notice that's the same as 15 over 1,500. So when I divide, I just get x equals 100. Okay, so I've got that. My next step is to verify that's where the maximum occurs. Again, an easy way to do it is look at P double prime. The second derivative is just negative 1.5. And that's less than 0. It's always negative. So that means it's concave down. That means it's a maximum. There's no place to plug in the 100 this time. And of course, if you look at that P of X function, it's just a downward parabola. We know that. But second derivative, that's why when we take the derivative, the second derivative, and we get the negative 1.5, it says it's always concave down because it's just an upside down parabola. Okay, so this 100, that is the number of units I have to produce to maximize profit. And they didn't tell us we're in any different kind of units or anything, did they? Nope. X price per suit, X number of suits, things in like thousands of units or anything. D says find the maximum profit and then find the price. So D, the maximum profit, well, what do? We take that, we know that maximum occurs when X is 100. We just plug profit function. So the maximum profit is just P of 100. Negative 0.75 times 100 squared plus 150 times 100. It's not 100. Minus 4,000. And we'll plug that into the calculator. Negative 0.75 times 100 squared plus 150 times 100 minus 4,000. I get $3,500. So there's my maximum profit. It's not what I said. I said $3,500. There's my max profit. And then E said, well, how many suits do we make? Well, suits, that's the quantity. Doesn't say the number of suits. It says what price should we make? Good heavens. I was just looking up. I already said 100 units. That was number of suits. E doesn't say number of suits. E says price per suit. Well, that was my P function. So that was way back up here. They gave us that. My price per suit is 150 minus 0.5x. So it's 150 minus 0.5, well, x was 100. So it's 150 minus 50, which is $100 per suit. So we found we make 100 suits, we sell them at $100 each, and we're going to get a profit of $3,500. Not too bad. Again, all of this is straightforward. There was no hard math that I did in the whole problem, but it's understanding all the steps and all the things you have to do. Okay, one last problem we're going to do. It's a little more involved than this. It doesn't have as many steps per se, but it's got some other stuff in it. So let me show you that. So let's grab that problem real quickly. So that's going to be this one. You see there's a lot of words here. And we'll paste it in right there. All right, maximizing revenue. Edwards University wants to determine what price to charge for tickets to football games. At $18 per ticket, attendance averages $40,000 people per game, excuse me. Every decrease of $3 to the ticket price adds 10,000 people to the average attendance. Every person at the game spends an average of $4.50 on concessions. What price per ticket will maximize revenue? How many people will attend at this price? All right, so let's go for this one. First of all, identify what we're trying to do. We're trying to maximize revenue. That's what the question asks. The question's always in the last piece of it, revenue. And notice that's what it says. What price will maximize revenue? That's what we're looking for. Well, revenue, again, price times quantity. All right, so here's where we have to be careful because the price is changing. So right now for revenue, what's the price? Well, right now they're charging $18 per ticket, but they're thinking about changing the ticket price. They're thinking about dropping the price in increments of $3 because it says every decrease in $3 to the ticket price. Well, we're going to let, where should I write this? I'll put this over here. Let X equal the number of $3 drops in ticket price. So think about what the price is. The price is $18, but they're thinking about decreasing it by $3 X number of times. I don't know how many times we're going to drop at $3, but that's all price. The quantity is the number of tickets sold. Well, they're selling 40,000 right now, but every time they decrease the ticket price by $3, 10,000 more people will attend the games. Now, I don't like the way that last one came out. So it's 40,000, but the attendance is going to increase by 10,000 people for every time we increase the price by $3. This is going to be my new revenue from ticket sales. We haven't done the concessions yet. But the reason I'm stopping here is because this last question. Oh, first question, what price per ticket? This right here is the price per ticket. And this is the number of tickets. But bear in mind, what haven't we done yet? We haven't added in the concessions. Well, the concessions are $4.50 per person that goes in there. So each ticket that we sell, we're going to get an extra $4.50. So what I'm going to do, our total revenue is going to be the price of the ticket, 18 minus 3x, but another 450 for concessions. That's going to be the total that everybody pays. That's going to be their ticket price plus the concessions. Everybody pays that much. Well, how many people? Oh, that's the 40,000 plus 10,000x. So if I do it this way, the first parentheses is everything that they spend. Well, the 18 plus the 450, I can combine those. What's that, 2250? So on average, everybody's going to spend 2250 minus 3 times however many times we drop the ticket price by $3. So that's how much revenue is coming in per person. The quantity of people is the 40,000 plus 10,000x. Now, if I was going to take the derivative the way that's written, I have to use the product rule. I don't want to use the product rule, but I don't have to use the product rule because I can FOIL this out. I know how to multiply two binomials together. It's not difficult. So let's think. 22.5 times 40,000. $900,000. Now, bear in mind this $900,000, that's how much they're getting right now in total revenue. We're seeing if we can beat that. We want to get more than $900,000 per game. So then I distribute that through. I get the 2250 times 10,000 means I move the decimal 4 places. So add 2 more zeros. So it's plus 225000. Is that right? 4 places? Yeah. So 225,000x, and then 40,000 times 3 is negative 120,000x, and then minus 30,000 x squared. These, of course, are like terms, so I'll combine those. Let's see. So I'm just checking my calculation on my calculator. And I get 105,000, which is what that says, but I did the other one so that I didn't make any stupid algebra mistakes. So negative 30,000 x squared plus 105,000 x plus 900,000. Again, that 900,000 is the constant. That means if we don't change the price at all, x is 0, those first two pieces go away. If I don't change the price, I get $90,000 as my total revenue. Let's see if we can beat it. Because what are the questions? What ticket price and how many people? Well, they're actually not going to ask us what the total revenue is. Okay. So first of all, find the ticket price. Well, if I'm trying to maximize revenue, what do? I have to take the derivative. So R prime, and I haven't been writing x, I'll just write it as R prime, negative 60,000 x plus 105,000. Set it equal to 0. I'll go negative 60,000 x equals negative 105,000. 60,000. Let's see, that's the same as 105 divided by 60. And I get x equals 1.75. Again, that's a critical value. I don't know that's where the max is. I can do the first derivative test, look to the left of that and to the right of that, make sure the graph's going up and then down, or just use the second derivative test, which is going to make it easier. R double prime is just negative 60,000, which is, of course, negative. So it's concave down, therefore it's a max. That's the second derivative test. If I wanted to do the first derivative test, remember what I'd do? I'd put the 1.75 here. And then I'd test a number to the left and the right. Say I test, I could test 0. Let's test 0. 0 is always nice. And let's say 0 and 10. I plug it into the first derivative. Well, the first derivative is right here. And if I plug in 0, I get positive 105,000, which means revenue is going up at that point. If I plug in the 10, I get negative 600,000 plus 105,000, which is a negative number, which means the graph's going down at that point. And since the graph goes up and then comes down, clearly I have a max in there. Since it's the only critical value, it must be the absolute max in that interval. So I can either do the second derivative test or the first derivative test, but I have to do one of them to show that it in fact is a maximum there. It could be just an inflection point, or it could be a minimum, I don't know. So I check. Okay, so I've got that. So I've got X is 1.75. The question was, what price? Well, remember, price is 18 minus 3X. I don't want to use blue there. Price, 18 minus 3X. And I just found X. So it's 18 minus 3 times $1.75. So let's see. 18 minus 3 times 1.75. I get $12.75. So what I'm doing is I'm dropping the price per ticket from $18 all the way down to $12.75. That's my price. And then the question says, well, how many tickets will we sell? Well, that's the quantity. And the quantity was 40,000 plus 10,000X. Number of tickets, 40,000 plus 10,000X. So it's 40,000 plus 10,000 times 1.75, because that's what X was. Ah, that was crazy. So 40,000. I guess I just need to move that decimal, don't I? 57,500. That's how many tickets I'm going to sell. Well, how many tickets did I sell before? 40,000 tickets. So now I'm going up to 57,500. We better hope that our stadium can fit 50,500 people. Otherwise, I shouldn't have lowered the price that much. So that's it. We found the price and we found the number of tickets sold. If we wanted to know the profit, it didn't ask for it, but let's find it. Because remember, we were trying to beat that $900,000. The maximum profit, where's our profit function? Oh, we don't have it. But it's going to be, oh, they didn't say maximum profit. They said maximum revenue. Let's change that. Because I don't know the cost. Max revenue. So for the maximum revenue, let's go to our revenue function, negative 30,000 X squared. What else do I have for revenue? Plus 105,000 X. Plus that $900,000. And so let's find the revenue when X is 1.75 and see if we beat our 900,000. Oops. That's what happens when you talk when you're trying to write. All right, let's put this into the calculator, see what we get. Negative 30,000 times 1.75 squared plus 105,000 times 1.75 plus $900,000. Ooh, I get a maximum revenue, $991,875. Now here's the good part. not only did we make more revenue, $91,875 more in revenue, but our costs are going to go down because we have fewer people coming to the stadium. So whether it's cleaning cost, whatever the costs are associated to that, we have fewer people. So we've even made more profit than we would have because our revenue's gone up and our cost has gone down a little. So anyway, that's the idea. There's 3 applications of finding absolute max or mins. One thing that a lot of people forget to do is to verify off to the side, like we did right here, either using the first derivative test or the second derivative test. We had to do one or the other to actually show that it is a maximum at that critical value. Otherwise, we just know that x is 1.75 was a critical value, but we were able to show that it was a max 2 different ways. You get to pick whichever one you want to. If it's a nice polynomial, the second derivative test is always really nice and quick to do. If it was a quotient rule, I definitely do the first derivative test because I don't want to take the second derivative at all. So anyway, practice these. They're going to take a little bit of work because they're just applying various things that we've learned. So just keep at it and remember, you can do it.